is our first official webinar on humidity. So the material we've chosen is useful for you, and we just to make sure that we cover definitely cover some basic definitions of humidity, and then also have some calibration suggestions for basically, I guess, tips and tricks and methods for successfully performing humidity calibrations. I'll be honest, humidity is not one of the easier disciplines to measure. It is such, and hopefully the material we have will be helpful. I plan on producing more webinar material for humidity, so if you have any suggestions, and depending on the questions we get today, then we'll know which we need to go. There is a lot of information out there that we would like to convey. So with that, here's the agenda, and we'll jump into it. So we'll go over some definitions of humidity. Let's see. Just something they can't hear. Steve, is there anything that, are you already on that? Okay. All right. Thank you. Looks like other people can hear. Okay. So this definition of humidity out of the text, we'll be looking at the first definition. One of the tricks with humidity is that there are so many different ways to define humidity, but basically it's an attempt to describe how much water vapor is in a gas, and most of the time the gas is air. That's what we are most interested in usually. Sometimes people in the gas oil industry also need to know how much humidity is in other gases like natural gas. So there are many different ways of measuring humidity. There is not an SI unit for measuring humidity. It's a derived measurement. We'll do that a little bit more here in a few slides. But some of these, well, actually, these descriptions we have here come up really useful measurement guide developed by NPL, by Stephanie Bell at NPL, and we have the reference here in case you'd like to go out and do more reading. I think it's a very useful information for those who are interested in measuring humidity. Let's just quickly go over some different ways that humidity is measured. First of all, it can be a fraction or a ratio. It's a proportion of water vapor in a gas volume. So it'll be a percentage or a part per million, describing how many parts of the system are water vapor and how many parts are the other real, the gas. So then there's dew or frost point. This where we measure the temperature at which the water vapor comes out of the gas and begins forming a dew or condensation. And the answer is that if you identify the dew point, if you know at what temperature the moisture will come out of the air, then use that value to calculate relative humidity, which we'll talk about here in a moment. But relative humidity is probably, I would say, is the most common indication of humidity. It's, in my opinion, the most confusing. But anyway, sorry for getting ahead of myself. And then constant is a lot like the first one that we talked about. This method is used by some national measurement institutes for reference level humidity work, where they will weigh the amount of water that's in a gas or in the air, and they can use that to calculate a relative humidity or a percent concentration or a fraction ratio. And then finally, relative humidity definition, and we apologize if all of you are already prepared and know exactly what relative humidity is, but we want to make sure everyone is on the same page, because understanding relative humidity is important for understanding the principles we'll be talking about for calibration or measurement. Is that a gas is saturated with water vapor. Chemistry tells at a temperature how water vapor like air can hold. And so when we measure how much water vapor is in the air, we can indicate by just to what percentage the air is saturated. And important is because it tells us a couple of things. In humidity measurements, one of the main reasons why we measure humidity, especially in manufacturing, is we want to make sure we don't reach a condensation point, because that's when a lot of damage can happen to products. But even before then, high humidity in general can be damaging to many materials or change humidity. And so relative humidity is useful because it can tell us how close we are getting to a saturation point where we will start getting condensation. Several years ago, when I was first studying relative humidity, I thought, well, really it's so confusing because you always have to consider temperature. And it's confusing, like here in Utah, you look at a humidity meter. We have a temperature and humidity indicator on the front of our building. And typical winter days in Utah, the relative humidity will be 70 or 80%. But our building has dry skin, having to use chapstick and lotion to try to keep moisture. And you look at but if you have a humimeter or gauge inside the building, the humidity is maybe 15% in an office space. Of course, in the cal lab, we have to put some moisture here. Anyway, so why is it that so dry when it's confusion ends up causing problems. People trying to figure out what the humidity is and thinking that the air in Utah in the wintertime is very humid. But anyway, like I said, it gets confusing. So I was talking to someone about it, and he said, well, one of the reasons why relative humidity is used in the weather report, and sometimes you'll also see the dew point reported in the weather report, at least here in the United States. But really is talked about a lot because it's what body senses it, because it's related to how much evaporation comes off of our skin. So the human body can feel relative humidity, if that makes sense. So that was interesting to note. Okay, so what are the used for in the calibration industry for calculating or measuring humidity? First, we have a general piece of instrumentation called the hygrometer, and that's simply a sensor instrument that measures humidity, and it can be a relative humidity sensor, like probably is the common, a dew point hygrometer, or a Psychrometer hygrometer, and we'll talk a little bit about these. And then of course there are many other ways of measuring the amount of water vapor in the air. It varies a lot. There's no single bird method, and there are some more common ones, and we will cover the more common ones in our webinar today. Another way that sometimes isn't mentioned is that you can generate a particular humidity, and because you know what the ratio is from your generation method, then, or if you know the pressure involved in the generation method, then you also produce a known value of humidity. So it's a method of measuring humidity, but it is a method of calibrating humidity in that. So relativity capacitive or resistive sensor that changes in resistance or capacitance depending on the amount of water vapor that's absorbed into the sensor. They will have a temperature sensor somewhere near humidity sensor. There's a picture of one over here, right? it's maybe kind of hard to see, but the small white, oh wait, I need to get a pointer going here. I forget the mouse pointer that I have doesn't necessarily work like you've shown me this before. This one? Or is it, it is that? I should have been more prepared. Sometimes it doesn't. Okay. If one of you would sending on the IM Instant Mesh tool there, if you can see this pointer that I'm using, I'm over here pointing to this picture on the right. This took the cap off so you can see that there's this small right. Yeah, I'm hearing that we can't see it, so Steve will check that out for me, and so I can start pointing around on the screen. At any rate, though, the small white square, it's hanging on a wire frame. That's temperature sensor, and then this large white just behind it, it's kind of ruler shaped. That's the capacitive humidity sensor. So it's fairly common that you will see a temperature sensor and a humidity sensor mounted inside the sensor. Of course, they come in many different shapes and sizes. They're embedded all over the place in industrial or manufacturing processes. And the typical accuracy or uncertainty associated with these varies quite a bit. That's good relative humidity source. Point hygrometers, these are common in a lot of calibration laboratories for measuring humidity. And what these devices do is they measure the dew point, so the point at which the temperature at which we reach, or that reaches saturation and begins to allow vapor to fall out of the system and collect as a dew or a frost. And this, as far as I know, dew point hygrometers, well, I have to admit there are some different techniques, but measuring the dew point, the most though is the chilled mirror device. And it's a chilled mirror because you can see in this diagram over here, a little metal plate, and it's polished to a shiny surface, so it looks like a mirror, and top of a heating and cooling module. And it's really fairly simple. I'm sure that the chilled mirror manufacturers would. I mean, obviously it's not extremely simple, but at any rate, you pass a supply of or a flow gas that you want to measure the humidity. You pass the air over the mirror, and you heat or cool the mirror until you see a fog or a dew form on it, and you detect the dew, the fog, or the frost is a bouncing light off of the mirror and then measuring the light that's reflecting off of the mirror. And so, of course, there are a lot of complicated techniques for controlling the dew point temperature carefully and measuring the light bouncing off of it carefully, control flow rate of the air. And at any rate, though, there will be a temperature sensor embedded in the mirror, and when the reaches get fog or dew on it, all we have to do is look at what the temperature sensor is saying, and then we have our dew point temperature. Let's go over the bullets really quick to make sure I'm covering everything. There are two main methods of measurement for chilled mirror hygrometer. Either air is pumped out of a sample and then is brought across the mirror, like you see in this diagram, or in instances the mirror is just placed inside a stream of air, maybe is inside of a chamber, a humidity calibrator chamber or something like that. So there are a couple of different styles of point hygrometer or chill mirrors on the market. In laboratories, the dew hygrometer or the chilled mirror is considered the reference standard. They usually have the best certainties as far as humidity measurement. And, typical accuracies are in the area of 0.05 to 0.5. It can be a little complicated determining what the true uncertainty or accuracy of the mirror is. You kind of have to piece together the specs that the manufacturers have and make sure you understand everything that's happening there. Like in my own research, and I noticed that some of them may not put the calibration uncertainty in their specs. They talk about actually more in the terms of it seems like it's more of a long-term drift, you know, a 12-month or 1-year repeatability or drift, and then you have to get the chilled calibrated from someone and then add in the uncertainty to that. One of the challenges of measuring the dew point is distinguishing between dew and frost on the mirror. One of the main challenges is that you have a nice clean mirror surface and you're running vapor over it, and those of you temperature, especially with fixed points, you know that oftentimes materials don't freeze right at their prescribed freezing point. So water is a example. You actually, if you have pure water, you actually have to undercool it or take it quite a ways below the freeze point to get it to finally start forming ice. And it's no different with frost on a mirror. Matter of fact, I've seen with our own chilled mirrors that even at dew frost point, again, it's hard to know where you're at when you're down in this region, but when you're below zero, low as -18, I've sometimes the mirror dew on the mirror, and sometimes it has frost on the mirror at -18. At 5, it's always dew from what I've seen. So it gets a little complicated, and some of the mirrors have techniques for forcing frost. You know, they will take the mirror all the way down to -30 or so to make sure they have frost, and then go back up to the dew frost point that's below zero, and the way they ensure they have frost on them. So it's not exact science. It can be a little tricky, and the reason why I bring this up is because, for example, at a dew point of -18, the point is -16. So there's a 2-degree difference between the two. So it can be a significant error if the chilled mirror doesn't know which one is measuring. Okay, other characteristics, usually because it's a complicated instrument, they're fairly expensive, and it can be very difficult to operate. They are finicky, or the mirror has to be clean, but then it's possible that it may get too clean for some chilled mirrors. They're sensitive if the mirror is too clean, and so there's definitely some art to measurement with a dew point with a chilled mirror. So another thing to consider is we'll show you some numbers here, but converting dew point accuracy to %RH accuracy is interesting. The sensitivity factors involved in that can have a really good, very accurate dew point measurement of 0.1 degree or 0.05 degrees, but humidities, by the time you convert dew point reading over to the equivalent accuracy in percent rates, well, you'll see what I'm talking about. It changes. It can be surprising how much that will change. And here right now, this is kind of a confusing table, so give me just a moment here to explain. These are examples of dew point uncertainties to %RH humidity uncertainties. So I have 3 different humidity points, or %RH points: 20, 45, and 95. The temperature, whenever you're measuring %RH, there always has to be a temperature indication along with it. we're just going to temperature at 23 degrees. That it does. Temperatures have a little bit of influence on these sensitivity coefficients, but not as much as humidity does. Then they go down. Steve, what color is this row? I'm a little bit colorblind and want to make sure I. Okay. And that sensitivity coefficient, the sensitivity, we have to have a sensitivity coefficient for converting dew point to percent RH, and then we also need a sensitivity coefficient for converting air temperature to relative humidity. They're pretty similar in size, but they can vary a little bit depending on the humidity. So right off the bat, you can see this low humidity of 20% RH, the sensitivity, the amount of change of percent RH versus change in degree C is 1.5. 5%, it gets 5.8, so it's almost a 6x or a multiplication of 6 to convert dew point to humidity. So now next row, where we have an uncertainty for hygrometers dew point measurement, uncertainty in dew points plus or minus 0.1 degrees C. And then to convert that to percent RH, we just multiply it by the sensitivity coefficient of RH to degrees C, and it is 0. So basically, it changes from 0.1 degrees C to 0.15% RH at 20%, but at 95%, it almost is bigger. So 0.1 degree accuracy in dew point is a 5.8% RH value or accuracy at 95%. So the other source that we need to account for in a dew point hygrometer. So the calibration uncertainty of the dew point hygrometer or the chilled mirror. The second one is the reproducibility of the chilled mirror, which basically the drift plus short-term non-repeatability. How does the chilled mirror reproduce the dew point? And that is assigned 0.1 degree C. That's a common spec with a lot of chilled mirror on the market. And then the other part of the chilled mirror is they always have a temperature sensor attached to them, so that you can measure the temperature of the air that's being passed over the mirror, because you have to have that value to be able to eventually calculate percent RH. And same thing, we have to convert that air temperature sensor uncertainty over to a percent RH. So the numbers can be a little different though, because the sensitivity coefficient is a little bit different for converting the temperature certainty to uncertainty in percent RH. And we combine these uncertainties and we arrive at this is an eye-opening for me. So this is a reference level humidity instrument, but at 95%, it's the systematic or total certainty for the measurement system in percent is 1%, would be pretty big for a reference level instrument. But carefully though, because I'm trying to set an expectation that in the humidity world, especially our humidities, the NCs can grow quite a bit, just basically because sensitivity of temperature as it relates to humidity. So hopefully, well, a copy of this table so you can look at this and absorb this a little more. Now, if you don't know what the sensitivity coefficients are for your own calculations, don't worry. The easiest way to get these values is just out on the web and find a reputable measure that has a dew point to humidity calculator. And then you can just experimentally load different values for dew point and see what the change in humidity is. And it's a fun exercise so that you can calculate sensitivity or determine sensitivity of temperature to %RH or %RH to temperature. I'm going to talk much about the psychrometer. I told someone to put this in here because I thought it was just an instrument, and they use it's kind of a creative way of measuring humidity. Basically, the principle is use a cooling effect of evaporation. So you have two different thermometers, and I wish I had a bigger picture of the one on the left. These are liquid and glass thermometers. One of them is mounted on both of them are mounted on a chain and a handle so that you can spin this thing over your head or to your side. Anyway, one of the thermometers is inside a sock, some type of water-absorbing material, and it's moistened, so it's wet, and that's called wet bulb. And the dry bulb, and you either swing these in the air to pass air over them, or you put them into, like sensor or this on the right. It's for the HVAC industry. So the probes are put a ductwork that you can measure the humidity inside of an air duct. But anyway, the thermometers are put into a stream and air is over them, and wet thermometer that's got on it starts evaporating, and that creates a cooling effect from the evaporation, and the cooling effect will drop the temperature of that thermometer. So then humidity is determined by the difference in temperature between the two thermometers. And another reason why I wanted this one on here is because a friend of mine who a few years ago was working as a forest firefighter in Utah. They were all required to learn how to use one of these psychrometers, the one with the chain on it. They were each assigned one so that they could take humidity readings while they were out monitoring the forest for dry conditions. And so he came to a Cub Scout meeting and showed all Scouts how to measure humidity the Forest Service way, or the forest firefighter way. And he had art that he measured. He would look up the air temperature and then the difference between these two thermometers and determine the humidity. So thank you out there, clarified that is a sling psychrometer. So so really quick. That for hygrometers are either the relative humidity sensor. This is the capacitive or resistive type, or the two-mirror hygrometer. Again, there are a lot of other methods of measuring humidity otherwise, but these are the most common. And then here are side-by-side comparisons between them. Some rate sensor is the speed at which they measure. So by the way, I happened to figure out how to get a pointer working. Right on that. Okay. Oh. Okay. I think you would. Oh, there we go. Got a laser pointer going. I was going to say, I think that would be one of these buttons to find on the screen. So any software engineers listening. Okay, now we should have a pointer going. Okay, thank you. Just got verification that it's working. So over here, this bullet with the R sensor. Keep in mind these things are made out of a lot of different materials, and some of the materials, well, two things: different sensor technologies and designs, and then different materials involved in building them. Some of them can require a lot of soak time to fully realize their accuracy, or to fully stabilize and measure to their specifications. Some of them are designed, though, to measure very quickly, or to have a very quick response time. So make sure you know what kind of sensor you're dealing with, because even ones that are slow, the majority of the change happens fairly quickly, but then you have this this runoff or I don't know, the roll-off effect that you can actually have a fairly long time constant. So there are also quite a few of them are very sensitive to contamination. So if you have volatile chemical air that you're sampling or in the vicinity of the sensor, you can cause them to drift quite a bit because of getting these chemicals inside of them. So when we talk about volatiles, we mean things that are really easy to evaporate the air. So even deodorizers or cologne and perfume, things like that can cause damage. I think one example I remember is a few years ago we our own dupers. For those of you who are familiar with them, we had changed to a different. We were in this nice little plastic case that had a rubber lining. Well, the manufacturer changed the adhesive inside of it without telling us, and so started seeing some that were drifting more, and we traced back to the vapor coming off of this glue was getting into the sensors and contaminating them. So that it can. That's one example of that. There's they're designed to be fairly portable. Usually, they're not considered an extremely portable device. They are mostly used in laboratories. Higher cost, of course. I think they start out in the thousands of dollars, or they're in the range of tens of thousands of dollars. But they are typically considered the most accurate method for measuring humidity and the most practical, most accurate practical method of measuring humidity. Be a little tricky to use. They have fairly fast response time, but then that can even be a little deceptive. You want to be careful with that. But they do typically have a fairly fast response time compared to a lot of the sensors. Okay. Now we're going to talk about the other side of humidity measurement. This is the humidity generator. There are main categories. There's the two-pressure humidity generator. We'll talk about what we mean by two-pressure, and then the mid-flow humidity generator. So let's jump into that. Two-pressure humidity generator. This is another interesting way of measuring humidity. We have two chambers. One is the saturator chamber, and this is where the air flow or the air is it's applied to a pressure and a water membrane that basically saturates the air with water vapor. And then we pass through an expansion valve and into the test chamber, and the chamber will be at or near ambient, and we measure the pressure of that chamber, and the gas goes from a higher pressure saturated gas to unsaturated gas, and the relationship of these two pressure values is related directly to the percent RH. So it's a nifty method of measuring humidity, or generating humidity, I should say. So let's see. There's more intricacy involved here, but at a high level, this is basically what's happening. Oftentimes, you'll hear someone talk about a two-pressure, two-temperature humidity generator, and it's called, and the temperature portion that is related to these two chambers the same temperature, but often they aren't because of either space or something happening here in the saturator, or because when the air expands, it cools down. For multiple reasons, there may be a temperature differential. So the temperature is also measured in each chamber. So the key in the test chamber is that temperature is measured close to where you are calibrating your humidity sensor. So you need multiple temperature sensors in the test chamber to make sure that you you know what the temperature is right where your sensor at. Okay, so that's a two-pressure humidity generator. Um, the two-pressure humidity generator characteristics are typically they are intended for laboratories. They are usually large mechanical systems with airs and cool systems, and they produce really good humidity uncertainties in the range of 0.5% RH, which is really good. To consider temperature non-uniformity of the measurement chamber, so make sure that you know what's happening in chamber, and that you map the chamber temperature sensors to know what the uniformity is. We use two-pressure humidity generators at Fluke, and we've some of our 17025 sensors that we still need another method of humidity measurement to verify that they are working correctly. So the science is very, very reliable. Every time we have checked them with another method, like with dew point, we get excellent results. But there is a possibility, though, that you know, temperature error or a pressure error, that there could be a humidity error. The systems are usually fairly slow to transition and stabilize in temperature and humidity, but they do once stable and at temperature and at the pressure, that the required pressure, they are very certainty. They also require a dryer source, so sometimes they'll have an onboard air, because you have to run up the air pressure fairly high, up around 100 psi for the separator, and it has to have a dryer on it. So be careful. Make sure that if you're using a shop air system, make sure that you have the air dried and clean, oil-free. And then here's the range of a two-pressure humidity generator. The humidity generator is a blower. It's a system that circulates air through a system and a humidifier system to achieve a particular humidity level inside the chamber. There will be a controller that determines how much dry air and how much moist air need to be pumped into the chamber to achieve the desired setting, and controlled and are traceable for humidity and temperature through a calibrated sensor that's inside the chamber. So let's talk about this in a little more detail. So they're called mixed generators because give them use a split stream principle like this one, where a supply of dry gas comes in and it is split. One goes through a saturator system or a wet flow system, and the other goes through a drying system. And eventually, the controller knows how much heat to load into the chamber to achieve the desired humidity. So the 51 humidifier uses a little bit different. This is a circulating and closed loop system. So a supply of dry air coming into it. It has on board an onboard humidifier and dryer, and air is pumped into the chamber and then brought back out of the chamber and through the humidifier, and then lies on the dry side. Air is circulated into the chamber and back out into dryer. So this is why it's called a closed loop system. This system is for achieving good stability, also using less water and less drying material to maintain the humidity level inside the chamber. Inside the chamber, there is a heating and cooling module and a fan that helps circulate the air and control the air temperature, so that we all can arrive at temperature set points. Let's see. What else? Temperature and humidity sensor is here in the chamber, and again, it's calibrated and provides stability, but also provides for the controller information for controlling temperature and humidity. So, because this is the first time we've heard much about the RHapid-Cal, let's just take a moment here and talk about some more features that it has to help humidity calibration. So some things to look here are the door has some twist-tight door ports to help create good height seals. There are different size grommets available for different diameter sensors. This is critical for any humidity measurement. You cannot let ambient air get mixed in to the chamber. So whether you're using a two-pressure humidity generator or a mixed flow, one of the most important parts of the system is the seal between ambient air or outside and the air inside the chamber. It also has an optional see-through door, so if you have to look at a display inside the chamber, then you can put the see-through door on it. We're planning on launching this product in Q of 2017, so we're excited about it, and it's part of why we're here today for this webinar. So, and these will be dealing with 17025 accredited calibrations, and so hopefully they will work well with a lot of people. So this summary of the humidity chamber or humidity generators. We've already talked about a lot of this. Let me just check and see if there are any highlights to hit here. And I do see a lot of questions rolling in, which is fantastic. That's why we enjoy webinars. We like to see all the questions. And mentioned it at the beginning, but I'll reiterate that we will review the questions at the end of the webinar. Oh, and I'm way behind. This is material, and first time I presented it, and I'm a little behind, so I need to speed things up a little bit. But I'll make sure we hang around to recover these questions. So don't worry. I just apologize. Some of you are on a schedule and won't be able to hang around afterward. Okay. So this is the thing we can just quickly go over. These are basic in a measurement and calibration system. We need to assign a measurement uncertainty or know what the measurement uncertainty is. I like a description of importance of uncertainty, because it basically says that the measured value is useless unless we can indicate the quality or certainty of that measured value. And measure traceability is, you already know, it's an unbroken chain of measurements that link an instrument's measurements to the SI, no longer defined as linking instrument's measurements to your local measurement institute. It's SI, or acceptable standard. And management is a calibration system that ensures a high probability of instruments being in tolerance. So some common components of the risk management system are TR 4:1, certainty 95%. Anyway, we're not talking about this stuff today. It's just a quick reminder of if you're working calibration and measurement to apply principles. So let's apply traceability to humidity. The traceability for relative humidity. We have a relative humidity sensor here. Has two paths of traceability. There we have the temperature side, which is very clear what that is, and it goes directly over to the Kelvin on the SI. And then we have humidity. That can be interesting the way it's traced through to the SI, because there's so many different ways of measuring humidity. It can either be by temperature, by measuring dew point, or by pressure, or by weight, and the list goes on from there. There are some mass humidity measurement that would not be traceable to the SI. So that's one of the interesting things about humidity. Okay, so consider that for those of you who need to ensure your traceability. Okay, so keys for successful humidity measurement. This may be one of the most important slides in the presentation, in my opinion. So these are some lessons that we've learned as we've been measuring humidity. First of all, the interesting thing about measuring humidity, and this is very, very useful. If this was the case, it would make things even more challenging. But fortunately, water vapor, when it's in a gas, will diffuse very quickly and evenly. And all of the literature I read makes it an instantaneous process. So, and I, from what I've seen, that seems to be dead on. I'm sure that a purist would have some particular scenarios where maybe this isn't always exactly dead on, but so where are the errors at? If the water vapor diffuses quickly and evenly in a system, why get humidity errors? And that's because of the temperature errors. So the gradients don't diffuse quickly and evenly like water vapor does. But during the air is one method of mixing the air are methods of helping reduce temperature gradients that are inside the air. And again, the relative humidity is an indication of the percentage saturation of air at a specific temperature. So you may have a particular water vapor mixed into a system, but if the temperature is higher on the left side than it is on the right side, then the relative humidity will be different, even though the of vapor to air is the same on the left and right side. It's because, again, it's relative humidity, so a temperature differential causes a difference in percent RH. We already talked about this. When you are measuring humidity, it's critical that the measurement area is, well, calibrate sensors, that it's isolated from ambient. So working with a chamber, make sure you don't have air leaks, and also make sure that you have proper immersion. So those of you who work in temperature know the importance of sufficient immersion for temperature sensors. Well, it's the same principle here. The humidity chamber is basically an air bath. You have to make sure that you don't temperature gradients from outside influence what's going on in the inside. Don't allow condensation to form. Okay, I think we've already talked about. So keep an eye on point. Expect humidities. Be careful with recognize that temperature and humidity inside the chamber may not get a dew point, but the temperature outside the chamber could air to quickly condense if they start interacting, and so you can get condensation in air, like on the door where the chamber and ambient temperature meet. With sufficient time, like one of our partners on this project who has spent his career working in electrical measurements, he said humidity, waiting humidity measurements to stabilize is like watching paint dry. And because he's used to the electrical world where you push a button and within maybe milliseconds or a few seconds, your measurement's stable and ready to go. So be prepared in humidity to wait. Keep an eye on materials that absorb and emit water. Sometimes you have no choice but to include these materials in your measurements, just so that you allow them enough time to stabilize or at least understand what's happening. And material good for humidity measurement are typically think Teflon and seamless steel for the highest levels of humidity measurement. So, okay, in the humidity and calibration industry, quite often are measurements that are done that are single point or spot check. This is where you go to a factory and you have a humidity sensor on a wall or installed in a system, and you basically spot check it at the current conditions, able to change the temperature or humidity, and so only able to spot check it. And then the other side of things is a multi-range, a typical calibration that we're more used to seeing. So the limitation of spot check calibrations is that you are at risk that other levels of heat out of tolerance, and you won't know for sure. This calibration method doesn't fulfill traceability requirements, where a specified range of humidities, traceability requires that you corner or bracket the range that you are applying in that process. But spot check is necessary if the sensor can't be removed from the where it's used at. So, and then because it's relative humidity on the temperature side, there may be some other things that happen if the temperature changes that are not observed with a single point check. Here is an app. We won't spend too much time talking about it, but here's a sensor that's used in a fairly typical temperature and humidity range. It's using a process that temperatures or is specified over the temperature range of 23 plus or minus 5, so from 18 to 28, and the humidity range is 10 to 50% RH. So instead of verification points would be to verify or bracket these ranges, and because it's relative humidity, now it gets complicated in, well, now temperature and humidity combinations do we need to measure? So to help with that, what we've been using is we calculate the dew point equivalent of the temperature and humidity combination, and we use dew point to kind of guide us. So make sure that we're measuring at the lowest dew point, and then we also make sure we're measuring at the highest dew point to help to the range. Same concept with dew point. We also found good success with if you're calibrating sensors to start at the low dew point and work your way up to higher dew points. That way you can control situations where you may be approaching a condensation point. And this you don't have to follow the dew point. It's just a suggestion to create an order sequence order. Okay, let's see. Transfer errors. This is a really important concept. So we have a drawing here showing a situation where we want to calibrate these humidity sensors inside a chamber. Keep that again, we're working with air, and air is not a good thermal conductor. We whisk these into a liquid would help, but we're working with air. And we have to watch out for thermal gradients that are caused by things like the cabling or the body of the sensor itself. And so we're calibrating, ideally, if we have a short sensor like this one, we go all the way inside the chamber and then have a cable coming out. There's other two scenarios where the sensor itself is protruding through the door into the chamber. This red arrow it describes where thermal gradients or thermal transfer is happening between ambient conditions and chamber conditions, and so we have to be really careful with that. And so the bottom one I would definitely be a risky measurement. The center one probably is okay. It looks like the red arrow doesn't all the way to the end of the sensor where the temperature and humidity sensors are at. And then is the ideal one if that's possible, but it's not always possible with sensors to have that luxury. So a little bit more about it. If you're to really to effective measurements, you really need to understand how the sensor is built. So we have different sensors. This is a Fluke Dukester. This is a full immersion sensor, and it's designed to just sit in a room in full immersion. And so there wasn't is basically the sensor is mounted to a fairly thick set of electronics, and there's high potential for temperature gradients to be passed along that sensor if one end is left at one temperature and the other end is inside a chamber. So sensor is intended to be a complete immersion. This sensor from is designed to be able to be immersed into a measurement system. And if you look at the design, the temperature sensor is built on a thermally isolating aluminum here. It's mounted on a wiring structure that has very low potential for thermal conduction. It helps to isolate the temperature sensor better. Looked at other sensor designs where the temperature sensors really on wires, very thin wire to help isolate it. And then, of course, humidity sensor, the interesting thing is it doesn't have a thermal gradient sensitivity. The humidity sensor just has to be in the area where it's at that you want to measure. So the humidity sensor isn't so sensitive. Up here on the Duke sensor, here's the humidity sensor. It's an C type integrated circuit humidity sensor. So I'm almost done. I just realized I'm already at 9 o'clock here. Just a couple more slides, and then we'll switch over to the question. So here's the particularly short temperature and humidity sensor on this meter. And so to measure it, if you want to extend it through a door, you have to use a thin door, but it's thin that it may not be extending into the working volume or the specified area of the chamber. And so if that's the case, you may need to account for what the temperature is right here near the door. You also be careful and make sure there's a good sill, because the sensor is so close to conditions, it would be very easy for air to leak in there and create a different level. Okay. Here's the entire unit of the chamber. The pros here is it may be difficult to reach in there and push buttons or take readings off the display. I drilled a hole in this door so that I could push if I need to with a stick. Worked really well. I switched over to the measurement method too with this particular instrument, and used a grommet and a piece of wire to put pressure on the sensor to push it against the door and create a nice sill. And I fortunately I got equivalent results between this method and the one that I showed previously. The door thickness allows about 2 centimeters of the sensor to go inside. So I was worried about thermal gradient effects from the door. Probably it's hard to see, but this is a temperature sensor that's mounted on wire, so it does have fairly good thermal isolation. But I was still concerned. But I checked the temperature right here by the sensor, and there was a little bit of thermal gradient effect, but not nearly as much as I thought there was going to be. So I was pleasantly surprised that this method also worked well. The advantage here is I could then, if I wanted to calibrate more than one unit at a time, I could drill more holes and install more grommets and mount more of them on the door like that. So because for the sake of time, I'll quickly go through this. This is basically a general procedure for measuring humidity, talking about installing a sensor, making sure that it's sealed, and then work your way through the temperature and humidity points. And here's a method of calibrating integrated sensor and units. Sometimes people call these pucks. That it goes the entire unit inside the chamber. And consider the things to watch out for here is that sometimes these things, the displays can put off some heat, so they can be tricky to calibrate. So be careful with those. Let's see. Laboratories will use a small camera inside the chamber to measure to readings off the display through OCR, which is an interesting technique. But also consider that if these things are fairly big, they may impair airflow inside the chamber and can cause temperature gradients. Another of a puck type or an integrated load inside the chamber. And here, methods of using external references in a chamber like this, where you interface dew point hygrometer shield mirror with it. Either head can be mounted directly into the chamber for remote head system, or air can be pumped out of the chamber, the shield mirror. And a system for calibrating the dew sensor with associated test accuracy ratios. Notice on the temperature side, the test accuracy ratio of chamber by itself are not quite good enough, so we recommend for the temp side that to get a better TAR to use a reference thermometer like this, like 1523 handheld thermistor probe. And with that, and again, I apologize for going over, but we've learned that we probably need to cut some material out of this, or we got a little too excited about humidity measurement. So I apologize.
I think that was a great presentation. Yeah, we do have lots of material here. Like Mike said, this is our first time through it, so we wanted to make sure that we covered a lot of the different aspects of calibrating these sensors. So we're ready now to take questions. We have quite a few. Mike, maybe what you want to do is just go to the top of your window here, and we'll start down through those, and then I'll check on as well.
Okay.
We'll answer as many as we can right now. I know we're running top of the hour, and if we don't get to your question, I'll send out the slides and link to the recording on Friday. And then if we didn't get your question answered, please respond to that, and we'll get you a response. So let's start down through yours there, Mike.
Okay. First question was when we were talking about a temperature hygrometer, someone asked, how can you have a dew point and frost point at the same time? That's an interesting question. I wondered about that when I first heard of it as well. And the way that works is, okay, there are two ways. One is you literally can have dew and frost mixing, so you actually have a slush. So that's entirely different. That's basically just has to be avoided. Situation where half the mirror has frost and the other half has dew. It can mess things up. But I think the basic question there is, I remember I said at a dew point 18, the frost is minus 16. And the way that works is you can, when you go below 0 Celsius into this point region, you can the dew point either as a frost point or a dew point equivalent, and there are some calculations out there to help with that. And part of that is there are some standards out there that actually require that dew point is always stated in dew point value regardless of temperature. But let me summarize this by saying that the temperature difference between the two is because there's water can. Okay, let me think about this for a second. it's the difference in water holding capacity of frozen or solid water, and that's put in the slides in the future is a little better description of what the difference is there. But basically, the reason why there's a temperature difference is because the capacity is different. If I had more time, I would go into that a little deeper. But if I have any other questions, I need to leave it at for now. But certainly get with me. I have more information on that. Let's see. When I get uncertainty at 20%, I get 0.24 times 2, not 0.24. Okay, let me go up and check that, make sure my is okay. Let's see. So you're referring to so you're converting dew point accuracies to percent RH at 20%. I get 0.4 times 2. Oh, I see. Okay, that's a good. I think what happened there is we didn't get that out to k equals 2, so that should be 0.48, where it says 0.24. All right, good catch. Thank you. We'll get that updated. Okay. Any level for dew point versus temperature or RH versus temperature chart? No, unfortunately, I went to like the NIST website. I have to admit, I haven't gone to MPL's website. They may have a calculator there, but I've checked several different manufacturers, Rotronic, Shell, Thunder, and I get the same results from all of their calculators. So if that helps with gaining confidence. We also have the equations ourselves. Contact me. I can give you to where those calculations come from dew point and relativity. Then you can make your own calculator as well. So RH sensor is reliable for measurement. That's a tough question to answer. I think there are a couple of really good. I really am impressed with the capacitive type sensors, and the sensors like the one that the Duke uses works well as also it's slower, but it works well for its design application of being in a room. So it provides really good repeatability, but it's just slow to respond to changes in humidity. Whereas the capacitive sensors, I'm impressed with how quickly they respond to a change in humidity. And then the I'll probably have to.
I can kind of respond to that. Yeah, there was a question in here about, we talked about mixed flow generators in general. Their U.S. list price is about $20,000 to $32,000. And then, as Mike mentioned, our product that we've been talking about, the 5128, it hasn't launched yet. It'll launch in first quarter, and the list price on that in the U.S. will be about $27,000.
Okay. Ability of a mixed flow generator. Well, the temperature stability that I've been seeing, I don't remember what the specification is off the top of my head, but temperature stability is in the well, I'm looking in terms of millikelvin, which is thousandths of a degree, but I routinely see stability of 5 to 10 millikelvin. Then the stability is I think the for humidity stability is 0.1% RH, and I really see that. Let's see. Oh, yeah, you're right. Okay, so When is the whole thing sent in or just the sensor? The Fluke chamber will the whole thing will be sent in for calibration. It'll be calibrated as a system. If you're being tend, well, I guess I can just read. I need to read it first before I. The 15% RH. What do you use to increase and maintain humidity in your cal lab? We have two main. We actually have a one room where we're currently using a portable humidity generator because it's particularly dry with cold weather we've been having recently. But really an in-duct system that we're using in our laboratory. It uses steam, heated water to humidify the room. So okay. Configure the 5128 to provide conditioned air to an external chamber. There are sample ports on the front designed primarily to take a sample of the air out and run it through like a chilled mirror hygrometer. You can see it could be pulled out and into another chamber. That's a good question. We haven't even looked at that as a possibility. That it may be possible, but that's probably not in the design criteria for it. But we have to take a look at that and get some more information. Okay, let's see. Salts. I have to admit I did not put any saturated salts information in here. And so I apologize. I'm not prepared to really talk about that much at this point. But I've heard of laboratories using them, and that the humidity traceability is provided. But I'll have to look into that. I apologize for not knowing more about it. As you can suggest for learning the art of chilled mirror operation. That's a very good question. Of course, well, we talked to multiple manufacturers. We've been using chilled mirrors from a couple of different manufacturers, and it's interesting how, like for example, one mirror that I'm using. I've been using all chilled mirrors and then also remote head. One manufacturer recommends very limited flow, almost static air on the remote head, but the manufacturer recommends turbulence and I've seen that in measurement that the two mirrors respond differently. It's really important to talk to the manufacturer and find out what they recommend. They talk about flow rate and whatnot in their manuals, but sometimes some of those details aren't in the manual. The mirror cleaning techniques varies from one manufacturer to the next, and that it's really important to talk to someone from the manufacturer and find out what they recommend. And one the manufacturer recommends when you cleaning the mirror with that you leave a little bit of water residue on the mirror and let it dry on its own. Don't so that the water is completely gone. And whereas you always clean the mirror very wipe the water off. So let's see. Calibrate the two-pressure chamber, and what is cycle? We rate our two-pressure system every 6 months, partially because we are using them right up to the limits of their specs, and we want to keep a close eye on that. And one of the things about a two-pressure chamber is that the calibration is done by calibrating pressure gauges. I would say that the two generators on the market also require temperature calibration. So I think in the we have to calibrate 5 or 6 temperature sensors on it, and also calibrate 2 pressure transducers for that. Can we do it every 6 months? But I would say that a 12-month cycle would probably be safe for a lot of labs. We use ours so much. We use both chambers every day, 24/7. So we get a lot of wear and tear, and that's one reason why we check them every 6 months. The temperature sensors kind of take a beating with what we do, well, because of the use that we put them through. How do you recommend condensation from the chamber before use? Well, for the first and foremost, you use a dry paper towel or towel and just wipe out any moisture. Open it up and use the moisture is gathered at the bottom of the and but then also you can run it through drying cycle. The Fluke recommended drying if you do reach condensation. They're designed to help you avoid reaching condensation. So if you again, it gets tricky with relative humidity. You can be measuring at a nice temperature and humidity, and then mistakenly change the temperature and quickly force the chamber into a condensation point. And the controller helps you avoid that. It's not completely foolproof. There are a couple of things you can do to still put it into condensation. And if you then basically you run it at a little bit higher temperature, a little bit above ambient, at a low humidity, and let it just completely dry out before you continue on through your calibrating work. How do you calculate the uncertainty budget of relative humidity? That's a good question. That's one of the directions we're contemplating going with our webinar series. Is maybe our next webinar will be talking about uncertainty calculation. The trickiest part is we'll convert temperature to %RH, and we give a clue there, or we use some typical sensitivity values that are used for those conversions. But we're planning on moving. We'll be in our material, and one of those most likely will uncertainty analysis in it. So, any fit points for measuring or calibrating humidity, like in temperature? Off the top, I don't. It's not in mind. In some ways, dew point is kind of like a fixed point. It's really a occurring point, and you just have to measure the temperature of it. That's the closest thing that comes to mind. So for example, he uses an S point to check his thermometer. Is there anything like that we could use to check humidity? And nothing's coming up. We mentioned earlier, someone mentioned the salt. Possibly that could be kind of like a point to check your sensors, but in our laboratory we just have a humidity that we keep as a check standard, and we check reference. So a fallback method is to have another reference to check it against. Okay. Is it okay to ask questions, Steve? Okay. Let's see. What's Sen 5128A? It's the Rotronic sensor. We showed some pictures of in the let's see. Do the recalibration of the 5128A. There is a calibration method described in the manual. Basically, it involves using a chilled mirror hygrometer. But to get a TOR on that, you have to. It gets a little tricky, especially the higher humidities. Getting the very, very good dew hygrometer, chilled mirror, and have it calibrated at a laboratory with really low uncertainty. We're going to NIST to have ours calibrated to be able to get a low enough uncertainty to get a good TUR. And even TUR is 2 to 1. Humidity is challenging science, and so it's kind of crazy that we have to go all the way to NMI to be able to get the uncertainty levels we need to even get a TUR of 2 to 1. Okay, let's see. Well, if we'll receive an attendee certificate. Okay, Steve says that he can generate one for you. If you will contact Steve, you'll have his contact information when he sends us out. Kicking around, aren't I, Steve? He's trying to keep track of all the questions here for me. Oh, how does the uncertainty of the RHapid-Cal, the Fluke RHapid-Cal, compare with a thunder chamber? The thunder chamber effect for a percentage at 0.5% RH. The RHapid-Cal is spec'd at 1% RH. And then percent at 95% RH. Okay. This is a good point that is making here. Why do most manufacturers define humidity accuracies only at 25 degrees C? That's why we put this in talking about traceability. That oftentimes that's what we a lot of instruments specified for humidity at one temperature, or they are only calibrated at one temperature. But for relative humidity, you have to cover the range of temperatures and the range of humidity. So the RHapid-Cal, for example, we are calibrating it at 14 different temperature and humidity 4 different combinations of temperatures and humidities to make sure that we thoroughly cover temperature range and humidity range. Interesting to see how things evolve. I've seen that humidity does act. You get slightly different results depending on the temperature that you're measuring at. So don't just assume that works well at 23 degrees C or 25 degrees C that it's going to work well at 20 or 18 or some other temperature. Does the 58 need an air compressor? No, it's a self-contained system. It has an onboard humidifier and desiccant cartridge, so it doesn't need a supply of air. And let's see. Another about the RHapid-Cal is what is the accuracy of the temperature and humidity probe. So the humidity accuracy is 1% RH, and the temperature sensor is 0.2 degrees C, plus degrees C. A question about comparing humidity results to the two pressure and mixed flow unit. So we'll get some more information for that and see how to put that into this. I see that's a common question, so they come up twice here. 28 again. All right, let's have that sitting here. While you look at that, we answer some more questions. Okay, someone's reporting the idea that it's important to use when we mentioned two pressure chamber, to make sure that you use multiple temperature probes inside of it to know what the temperature is exactly at the point of where your sensor is located. So we appreciate that. Any other questions on your side? I'm pretty much at the end of the list that I have.
Yeah, there are a couple more good ones here, Mike, and then as we mentioned, we may have missed some, so please do not want to send out the slides if we haven't covered yours. Here's one. Maybe I'll just read that.
Okay, it says, do you have issues with calibrating RHers at both a nominal humidity of 50% and then later on having to recalibrate due to humidity going down to 5%? There are others that we calibrate and find that the calibration performed in not out of tolerance. Oh, now that the humidity has gone down, that they show out of tolerance. Oh, that's interesting. I would definitely check those RTDs for leakage. Hold our metal sheath so that you can connect a resistance meter sheath and then the other probe over to one of the lead wires of the sensor, or with that with leakage as well by doing. I guess it doesn't matter which one you start with first, but you can put the probe at a temperature that's well below zero, like minus 40. That will definitely create a negative pressure and cause to pull moisture inside the sensor. Checks it changes at the idle point of water, and then heat up to a temperature above 100 to drive your out of it, and go back and measure the ice point or the triple point and verify that the resistance is changing, and then that will help you determine if then it's leaking ambient air into it. Then you probably will see difference in results depending on the humidity of the ambient air. Okay.
Another question, Mike. I don't know that we addressed for sure. We kind of alluded to it, but can you use chilled mirror with the Fluke 5128 to improve its accuracy? And then would that be close to a two-pressure system if you did that?
Absolutely. You can use a reference chilled mirror with it to improve the uncertainties. If you back up to this slide, it gets a little tricky though. It's not as awesome as I originally thought it when I separation of chilled mirrors from these humidity sensors. There isn't as much separation as I thought at the higher humidity. So to demonstrate that, we'll look at the slide. Certainly down at the lower humidities, like 20% and 45%, the chilled mirror has a % RH accuracy of about 0.5%, which is dead on with what the pressure. However, up to 95% RH, the sensitivities start killing you, or start killing the uncertainty. So you quickly drive the uncertainty up close to 1% RH, which is not. The two pressure humidity uncertainty 0.5% across the whole range of. I know. Well, something that can be done, and they're planning on doing in another webinar, is methods and uncertainties in humidity measurements. But something that can be done is here for the temperature portion of that, you can make an impact by bringing in a different temperature so that has better specs than 0.1, and that'd be easily done. Even the hand instrument thermistor probe that we were showing earlier would significantly increase or improve. So you could decrease a portion of the uncertainty challenge. This 0.6% RH for the cal uncertainty and also for the reproducibility is tough. And then I want to say too, this cal uncertainty of 0.1 degree C dew point, that's not exactly easy to achieve either. I checked with several with multipliers of accredited dew point calibrations, and 0.1 was about the best I could find. Some of them were in the 0.2 to 0.3 degree C range. That's part of the reason why I went to NIST, because I have a very low uncertainty dew point calibration process. So the other thing is that you could have the chilled mirror calibrated with a really low dew point uncertainty.
Okay.
To make it competitive with the two pressure generator at 95%. I guess to final answer that question.
Okay, good. One last one, Mike. There are a couple of questions on needing consumables like desiccants. Maybe you want to comment on that.
Oh, okay. We've been experimenting with a couple of different desiccants, and I suppose all of them can be generated in an oven. Some of them start crumbling apart if they're held, whereas other ones are showing their integrity as far as not crumbling apart and maintain shape and whatnot as they are dried. Some of them have color changing chemicals added to them that the process doesn't reverse with some of them when you dry it out, so you lose the indication of how much moisture is in the desiccant. I'm not sure yet what final will be for the RHapid-Cal. The good news is we've noticed that materials work well. It's narrowing down what works and what. But the plan to have a available cartridge is taken out, dried, or just replaced, I guess is maybe where we're still not sure exactly what we're going to recommend, but it will be a refillable cartridge. Or there may be a cartridge available too that's just you fill it, you just buy it, use it, throw it away, and buy a new one. I'm not what will be the final available options.
Okay,
Steve's
great.
nodding his head, so
no, we still got a little work to do, but like you said, the goal is to get it so it's a readable cartridge, have that available.